So the sun, it's pretty hot, pretty bright. And in fact, it's pretty bright because it's pretty hot. Now, just how hot is it? Well, it's about 5,700 degrees K at the surface. And a guy a while ago, I can't remember which scientist this was, but it was an interesting experiment. He actually took a block of ice and he put that block of ice in the sun and he measured how long it took the direct sunlight to melt that block of ice. And he knew how much the heat capacity of water was. He knew the transition temperature and the transition heat of ice to water. And he was able to then calculate how much power it took to melt that block of ice. And then he said, well, okay, now take that block and turn it into an equally thick shell around the sun with a radius of the Earth's orbit. And that shell would melt in the same amount of time. And then he calculated the mass of that shell and determined the power output of the sun. And, well, the power output of the sun was something on the order of 4 times 10 to the 26th watts, which is, a fair bit of power. Now, what could be producing that much power? Well, that's a bit of a problem for, guys in the mid-1800s. They had no clue. It couldn't be a chemical reaction. No chemical reaction could put out that much power for the length of time that we kind of knew that the sun had been shining. And back in those days, we knew that the sun had been shining for at least a few million years. We had no clue it was 4.5 billion. But never mind that. They didn't know what that power output could be. And it was Eddington, I think it was. Eddington figured, well, maybe it's just plain old gravitational collapse. If you imagine that the sun is a big sphere of hydrogen with a radius of the Earth's orbit, right? So great big ball, and it fills the whole Earth's orbit. And then it begins to collapse under its own gravitation. Well, just the heat generated from that would power the sun at its current rate for something like 10 million years. And that was satisfactory until we started realizing that there was, rocks that were, a lot older than that. So what does power the sun? Well, nowadays we know, of course, it's nuclear reactions that power the sun. In fact, in particular, nuclear fusion. Nuclear fusion of hydrogen into helium. Now, this only occurs in the innermost 10% of the sun, right? In the core of the sun, where the temperatures reach ridiculous levels of things like 15 million degrees K, right? Really, really hot in there. And the pressures are enormous because you've got the entire weight of the sun sitting on the core. So, high pressure, high temperature, perfect place for hydrogen fusion to take place. Now, why is hydrogen fusion so difficult? Well, first of all, the temperatures are so high that the electrons are just gone from the hydrogen atom. They're just free to roam. They're not going to bind any hydrogen atoms. Just too much energy down there. The protons, the nuclei of the hydrogen atoms, all repel each other. They don't want to be close to each other. They're all positively charged. They're all trying to keep as much distance as possible. But the temperatures and the pressures are such that every once in a very great while, 2 protons will approach to within 10 to the minus 13th centimeter. And at that distance, the strong nuclear force takes over, which is very attractive, and it binds those 2 protons together and locks them together into a single unit. And the 2 protons still don't want to be near, so one of them throws off a positron and becomes a neutron, and that positron finds an electron somewhere and annihilates it, and you get a lot of gamma rays, and there's a lot of energy, and that is going on in the core of the sun right now. And there is enough hydrogen in the core of the sun to maintain that reaction for 12 billion years, of which we've used up about, 4.5 or 5 or something like that. So plenty of fuel left. The reaction continues on. The the hydrogens that bound together turn into a deuteron, that's a proton and a neutron, and then two deuterons will bind into a helium nucleus, and then the helium nucleus just falls to the center of the sun and sits there, sullen, doing nothing, can't do anything, and not going to react with anything, it's just going to sit there and take up space. And because it's taking up space, it slows the reaction, right? So, the sun's core is producing helium. All that helium sinks to the center of the core, takes up space, blocks the space for the reaction to occur, and therefore the reaction slows down, which causes the sun to collapse. Because the thing that's holding the sun at its current size is this outgoing force of radiation and pressure. Well, if the sun cools just a little bit, then the sun contracts a little bit. But when it contracts, it heats up the core and it increases the pressure, and that raises the reaction rate again, and it all stabilizes. So the sun is sitting in a state of dynamic equilibrium, burning fuel as fast as it can to stay the same size. And by the way, failing at that, eventually that helium nucleus is going to win. And as that helium nucleus, that little core of helium, the nugget of helium in the core of the sun, as that thing gets bigger and bigger, well, the sun gets hotter and hotter, right? So the sun is getting hotter. It's about 10% hotter than it was when it formed right now. In fact, the Earth is no longer in the Goldilocks zone of the solar system, right? It's too hot now. The Earth's orbit is too close to the sun now. It's too hot here. If we did not have life on this planet, the oceans would evaporate and life, things would not be good here. But life produces the gases and the substances that keep the Earth in temperature equilibrium. It keeps the Earth cool. What life is that? Well, mostly plants, because they suck the CO2 out of the air, right? So CO2 can't build up, and the temperature continues to diminish, right? So it is life that keeps the Earth habitable for the moment. Now, that's going to break down in about a 250 million years, maybe another 250 million years, maybe 400 million years, at which point the sun will be too hot and the oceans will evaporate and life here will be impossible. So we'll have to probably move the Earth if that ever happens, right? If we move the Earth, out towards the orbit of Mars, that would be better. Yep. So anyway, that's what we've got to look forward to.